A conventional autocannon firing at this rate melts its own barrel in under 2 seconds. The GAU-8 Avenger solved that problem by distributing the load across 7 barrels, rotating at 100 revolutions per second. What it created instead was an aircraft that had to be redesigned from the nose gear up just to survive firing it. The gun that defines the A-10 was not designed to fit the aircraft. The aircraft was designed to survive the gun. That distinction shapes everything about how the weapon works. A conventional autocannon operates on a single-barrel principle. One chamber, one firing cycle, repeated as fast as the mechanism allows. The constraint that makes this principle fail at extreme rates is thermal. Every round fired deposits heat into the barrel liner, the rifled steel tube that spins the projectile on its way out. At 10 rounds per second, sustained for several seconds, the liner temperature climbs toward the threshold where steel begins to erode rather than resist. The projectile's copper driving band strips microscopic material from the liner with each pass. Accuracy degrades first, then the liner fails. A conventional 30mm autocannon attempting to sustain 70 rounds per second would destroy its own barrel in under 2 seconds of fire. The rate that makes the weapon decisive makes the barrel lethal to itself. The GAU-8 Avenger solves this with a principle that predates aviation entirely. Richard Gatling's original observation, proven across 150 years of development, was that the thermal load of rapid fire could be distributed across multiple barrels if each barrel handled only a fraction of the total cycle. The GAU-8 uses 7 barrels arranged concentrically around a central rotor, each structurally independent but rotationally linked through the rotor assembly, driven by a single hydraulic motor. The rotor spins at 100 revolutions per second, roughly the operating redline of a high-performance car engine under full load. At that rate, each barrel passes through the firing position approximately 10 times per second. That is slower than a standard service pistol cycling at its designed rate. The individual barrel does not experience a weapon firing 70 rounds per second. It fires once, then waits through 6 full rotor positions before it fires again. Those 6 positions are not idle time. Each one corresponds to an active stage of the operating cycle. After firing, the barrel rotates to the extraction position, where a mechanical extractor pulls the spent casing from the chamber. The next position ejects it rearward into the feed system's return track. The barrel then passes through 2 indexing positions where the feed system aligns the next live round with the chamber entrance. At the 5th position, the bolt drives that round fully home and locks behind it. At the 6th, the system confirms seating. Then the barrel returns to the firing position. 7 barrels, 7 positions, 7 stages running simultaneously. While 1 barrel fires, 1 extracts, 1 ejects, and 4 are cycling through the feed and chamber sequence for the round that fires next. The combined output is 70 rounds per second. No individual component in that system is being pushed past the rate that would destroy it. The rotor speed that makes this work also defines the tolerance window the system cannot cross in either direction. Too slow, and the interval between each barrel's firing cycles shortens relative to its heat dissipation rate. Liner temperatures climb toward erosion thresholds within the first sustained burst, and the weapon begins destroying itself from inside the barrel steel. Too fast, and the bolt does not complete its full travel distance before the rotor indexes the next chamber into the firing position. The firing pin then strikes a round that is not fully seated. That is not a jam. It is a high-pressure detonation inside a partially open chamber, and the energy it releases travels immediately outward through the gun mount into the aircraft's forward fuselage structure. But rotating the barrels is only half the problem. Getting 70 rounds per second into those barrels without tearing the feed system apart is an entirely different failure waiting to happen. Conventional linked ammunition, the belted system used by most aircraft cannon, connects each round to the next with a small metal clip. As the weapon fires and strips rounds from the belt, those clips eject as a stream of small, irregular metal pieces departing the aircraft at unpredictable angles and velocities. At 10 rounds per second, the ejection mass is manageable. At 70 rounds per second, the system produces 70 link ejections per second. each one a candidate for engine ingestion, each one a small asymmetric mass departure that compounds across a burst into a measurable disturbance in aircraft stability. A single brass link ingested into a TF-34 engine intake during a strafing pass does not cause a warning light. It causes a compressor stall. The GAU-8 does not use links. The rotor completes another revolution. 7 firing events arrive so close together they register as a single tone, a low, grinding note that vibrates through the airframe before the ear resolves individual shots. The gun mount flexes with each cycle. Then the rotor decelerates. The tone drops. The air carries burned propellant. The system that replaces linked ammunition is a drum, but not a simple cylindrical magazine. It is a precision-machined helical track assembly that guides each round from its storage position through a continuous curved path to the chamber entrance, that then returns the spent casing on a parallel track into the drum body, all without a single connecting link between rounds. The drum operates as a double-ended system. One helical channel feeds live rounds forward toward the gun. One channel returns spent casings rearward into the same drum body. Both channels run simultaneously during sustained fire. The track architecture is what allows the GAU-8 to sustain 70 rounds per second without generating a single loose piece of metal inside the aircraft. Everything that enters the drum as a live round exits it as a spent casing. The aircraft carries its own brass. The rotor is turning. The barrels are cycling. But the feed system is only as reliable as the round it was built to handle. The PGU-14/B armor-piercing incendiary round measures 30 millimeters in diameter and 9.87 inches in overall length, roughly the dimensions of a standard wine bottle from base to neck. That comparison understates the engineering inside it. The projectile is a sub-caliber penetrator seated inside an aluminum outer body, a rod of depleted uranium alloy machined to a diameter smaller than the cartridge case, wrapped in a lightweight sabot that falls away after the muzzle. Depleted uranium carries a density 1.7 times greater than lead. At the muzzle velocity the GAU-8 generates, a conventional tungsten penetrator deforms on impact. The nose flattens, energy spreads outward rather than inward, and penetration depth decreases. Depleted uranium behaves differently. The impact pressure causes the leading face to shear away in a controlled pattern rather than flatten, continuously exposing fresh, sharp material as the rod pushes through armor steel. The penetrator sharpens itself as it kills. Against the upper hull of a T-72, the PGU-14/B does not punch a hole. It collapses the armor inward and drives fragments through everything behind it. The drum holds 1,174 rounds. At approximately 1.5 pounds per round, the ammunition alone accounts for nearly 1,760 pounds of the system's total loaded weight, heavier than a large touring motorcycle sitting in the forward fuselage. As the drum empties during a mission, that mass shifts the aircraft's center of gravity measurably rearward. Fuel burn rates on extended close air support missions are planned around this weight change. Because an aircraft whose center of gravity migrates outside its envelope during a low-altitude strafing run does not give the pilot a warning before the handling degrades. The aircraft doesn't announce recoil the way the numbers suggest it should. During a 1-second burst at full rate, the GAU-8/A generates approximately 9,000 pounds of rearward thrust. One of the A-10's 2 TF-34 GE-100 engines produces roughly 9,065 pounds of forward thrust at military power. A full-rate burst is, in net terms, the equivalent of shutting down one engine and replacing its thrust with a force pushing the aircraft backward. The aircraft continues forward because both engines combined exceed the recoil load. But the force is not symmetric, and symmetry is what determines whether the gun shoots where the pilot aims. The aircraft doesn't eject spent casings overboard, and the recoil load is not managed from the aircraft's centerline. Both facts solve the same underlying problem. If the GAU-8 were mounted with its geometric center on the aircraft's longitudinal axis, The firing barrel, one of 7 positions in the rotor, would sit offset from that axis by the rotor radius. Every shot would produce a lateral moment, yawing the nose away from the strafing line mid-burst. The engineers solved this by mounting the entire gun assembly 2.5 inches left of center line, positioning it so that the firing barrel, the specific barrel occupying the 6 o'clock position in the rotor at the moment of ignition, aligns precisely with the aircraft's thrust axis. The gun is mounted off-center so that it fires on-center. He's too far left, and the asymmetric installation alters roll and yaw characteristics across every flight regime, not just during firing. Too far right, and the lateral moment returns, compounding with the torque effect from the rotor's clockwise rotation during sustained bursts. In 1 second, the rotor completes 100 full revolutions. Each of the 7 barrels passes through the firing position approximately 10 times. 70 rounds leave the muzzle at 3,240 feet per second, roughly 4 times the speed of sound at sea level. At a 200-meter slant range during a low-angle strafing pass, the penetrators reach the target before the sound of their own firing does. The pilot is already climbing away when the first round impacts. The gas-operated bolt system taps propellant gas from each barrel at a point approximately 2/3 down the bore, diverting a controlled volume of high-pressure gas rearward through a port to drive the bolt carrier back against its spring. The timing of that tap determines how much gas pressure reaches the bolt and how fast it travels through its full operating stroke. Too much gas and the bolt slams rearward hard enough to bounce off its rear stop and begin closing before the spent casing has fully cleared the extractor, forcing a round into an occupied chamber. Too little and the bolt does not travel far enough to cock the firing mechanism for the next cycle, and the barrel rotates to the firing position with an empty chamber while the round waiting behind it sits undelivered. The pilot's hands register the burst before the ears process it. The rudder pedals carry a fine vibration, not turbulence, not engine noise, but the specific frequency of 7 firing events per 100 milliseconds transmitting through the gun mount, through the forward fuselage frames, into the cockpit floor. The aircraft decelerates slightly, measurably, the momentum of 9,000 pounds of rearward thrust arriving as a gentle but insistent push forward against the harness. Then the trigger comes up, the tone drops, the rotor does not stop, the Maverick missile gets more screen time. The laser-guided bombs get more footage. Neither one is why this aircraft exists. The smoke problem does not announce itself. At full-rate fire, 70 rounds per second generate a combustion gas cloud that expands from the muzzle faster than the aircraft is moving forward. At shallow attack angles and low airspeed, the leading edge of that cloud reaches the TF-34 engine intakes before the aircraft has moved clear. Combustion gases entering a turbofan compressor do not cause a gradual power reduction. They collapse the compression wave. Both engines can flame out simultaneously. The solution is not a filter or a duct redesign. It is burst limiting. The fire control system restricts continuous trigger down time to intervals short enough that the gas cloud dissipates before reaching the intake plane, and attack angle discipline absorbed during training until the restriction becomes reflex. Every pilot who flies the A-10 learns the gun's operating limits before they learn its effective range. The rotor does not stop when the trigger comes up. The hydraulic motor driving the rotor at 100 revolutions per second requires time to decelerate against inertia. Rounds already indexed into the firing position complete their cycle. Approximately 40 additional rounds leave the muzzle after trigger release before the rotor slows enough to stop the sequence. The pilot accounts for this before the trigger goes down. The attack geometry, the slant range, the burst duration, all computed with the overshoot factored in. The gun does not stop when the pilot decides to stop. The pilot decides to stop 40 rounds early. The rotor's clockwise rotation, viewed from ahead of the aircraft, produces a counterclockwise moment on the airframe during every burst. The pilot corrects with right rudder input, a small deflection that becomes automatic after enough range time. New pilots walk their first live burst left of the intended aim point before the correction becomes reflexive. The aircraft does not warn them. It tracks where physics dictates. The gun was specced before the aircraft had a name. Everything designed after that point was an answer to one question: how do you keep this weapon flying? The Air Force issued the AX program requirement in 1966 with the GAU-8's dimensions as fixed constraints. Fairchild Republic did not receive a gun to install in a finished aircraft. They received a set of envelope limits: diameter, length, weight, recoil load, and built the A-10 outward from those numbers. The fuselage cross-section at the nose was determined by the drum's outer diameter. The nose gear sits 9 inches right of the aircraft's center line, roughly the width of a human hand, so that when the gun occupies its operational position, the firing barrel aligns with the longitudinal thrust axis. Every structural frame forward of the wing carry-through was designed to transfer firing loads rearward into the airframe rather than absorb them locally at the mount. The aircraft's 57-foot wingspan was sized wide enough to provide the stable low-altitude platform the gun's attack geometry requires at typical combat range and airspeed. The titanium bathtub surrounding the cockpit weighs approximately 1,200 pounds, close to the weight of a concert grand piano, and it is not purely protective armor. The forward section of the tub serves as a primary structural member in the fuselage load path. Firing loads from the GAU-8 mount travel through the gun cradle and into the tub's forward face before distributing rearward through the main frames. Remove the tub and the aircraft loses pilot protection and a meaningful portion of its structural integrity under firing loads. The armor and the airframe are the same component. The engines sit high on the rear fuselage, intakes elevated well above the muzzle plane. This placement keeps intake faces as far as possible from the gun gas cloud during typical attack profiles. It also reduces the infrared signature visible from below and keeps the engines out of the debris field from ground fire striking the lower fuselage. Every positioning decision that appears to be about survivability is also an answer to the gun's operating requirements. The two constraints converge on the same solution. Rate selection determines what the weapon is being used for. At 2,100 rounds per minute, the shot pattern at typical combat range spreads across an area larger than a tank's upper hull. Individual rounds may fall outside the roof plate's vulnerable zone, producing non-penetrating hits that announce the aircraft's position without mission effect. At 4,200 rounds per minute, a half-second burst at 200-meter slant range concentrates enough rounds within the roof plate area to guarantee penetrator impacts through the vulnerable zone. Against light vehicles or personnel, that density is unnecessary and exhausts the drum against targets. A lower rate defeats equally well. From the ground, the sound arrives before the aircraft is visible. A low, grinding note, sustained for under a second, then gone. The A-10 emerges from behind it, now already climbing, gun smoke trailing in a thin horizontal line that holds its shape in cold air longer than seems possible. The note drops as the aircraft gains altitude, then silence, and the smoke dissipating, and the ground unchanged. The aircraft exists to deliver that half-second of fire. Everything else, the loiter time, the redundant systems, the armor, the low-speed maneuverability, is infrastructure built around one mechanical event. The gun is not a feature of the A-10. The A-10 is a feature of the gun. That logic runs through every design decision. The straight wing maximizes loiter, which gives the gun more opportunities per sortie. The redundant flight control systems exist so the aircraft survives battle damage and returns to firing position. The high-mounted engines stay clear of gun gases. The titanium tub transfers firing loads and protects the pilot with the same structure. The enormous fuselage volume holds the drum. The A-10 is not a platform that carries a gun. It is a gun delivery system, and everything else aboard is either a way to reach the target or a way to survive doing it.